Okay, good morning. We'll start. Okay, so today will be quite an important lecture. So we'll talk about attention and transformers. So basically, this architecture that we'll see today is what is driving everything that you are seeing in the news about AI. Almost any model now is based on the architecture that we'll cover today, the transformer architecture. So I will present it first as a way to solve a specific problem, which is historically the problem it was used for. It was used for initially to do machine translation, so to go from one sequence in some language like English to another sequence in French. But we will see that actually this architecture is not limited at all to sequences. And actually, strictly speaking, it's not even made for sequences. It's made for sets of elements, of tokens. But I will present it in the context of sequences first, and then we'll generalize it to images. And 2 weeks from now, during the lecture on graph neural networks, I will also tell you that this thing generalizes to other things like sets. Okay? So we'll go step by step today. I will first introduce you to the encoder-decoder architecture, generally speaking, which is something we've already seen briefly last week when we talked about the UNet architecture, to go from an image, then we were processing this image into a compressed representation of this image, and then back to the original spatial dimension to produce, for example, a segmentation mask. So we'll talk about that, but in the context of sequences. Then we'll talk about the attention mechanism, which is basically a new kind of layers that we'll see. And then finally, we'll see how to compose these attention layers to obtain transformers. Okay? And really, these layers, they are very fundamental. You should see them as fundamental as fully connected layers or convolutional layers. And actually, they are so powerful that you can even, in some cases, consider replacing entirely fully connected and convolutional layers with attention layers. Okay? All right. So let's start maybe with a bit of motivation. So if some of you, I mean, all of you supposedly have been thinking about project ideas, and maybe some of you have been thinking about ideas involving sequences of data. And that's very common. So you could have, for example, problems where you have a sequence as input, and what you want to produce, for example, is a classification or a regression value. Okay? So for example, if you take the case of a piece of text and you want to determine the sentiment attached to this piece of text, that's a classification task. You get as input a sequence of words, and what you want to predict, for example, is the class, positive, negative, or neutral. That's the same if you are dealing with videos and you want, for example, to detect actions or events in these videos. The videos are inputs of frames, okay, but so there are sequences of frames, of images, and what you want at the end is to classify, for example, the entire video, the entire sequence of frames. Another example of sequence classification would be sequences of DNAs that you want to classify. For example, if you think this sequence is associated to some disease or not. Okay? So conceptually, in this first set of tasks, what we'll have is that we are given as input a sequence of elements, which I will represent by these rectangles. Usually, in the context of sequences, we call these elements tokens. Okay? And we assume that we have T tokens. And a notation that I might use is the following to denote a sequence starting from 1 to T of elements X, okay, which themselves are tensors. Okay? So the first kind of task is that you want to take this kind of thing as input and then produce, for example, an element, a class, or a vector of probability estimates, or you want to produce regression values in some space. Okay? The Other machine learning problem you could be interested in is what we call sequence synthesis or sequence generation, which is about you just want to generate new sequences. For example, you want to generate pieces of text, you want to generate music, you want to generate videos. All of these things are examples of sequence synthesis. And here the difference is that you would start usually by just some fixed input, fixed size input, and you want to map that to a sequence. Okay, so this would be classification, this would be synthesis. And finally, the last example of problems involving sequences is when you are given as input a sequence of tokens and you want to produce as output another sequence of tokens, which could be a different of different nature. Okay, so this would be a sequence-to-sequence problem. So if we want to formalize this a bit mathematically, I will denote as calligraphic X the set of sequence elements or the set of tokens, so the set of possible rectangles. And I will denote as S of X the set of sequences I can build from this set of basic elements. Okay? So it's the union of all possible compositions of these tokens. And once we have this notation, then we can say that the sequence classification problem is the problem of finding some function which maps an element of the power set of the token, so of the set of sequences, to, for example, a vector of probability estimates. The sequence synthesis problem is a problem where you start from some fixed size vector, and you want to produce as output an element of this set of sequences, so you want to produce a sequence as output. And the sequence-to-sequence translation problem is the problem of finding a function which maps a sequence from some set of sequences to another sequence to another set of sequences. Okay? And so you see that the two sets of sequences, they do not need to be the same. Okay, so you could have, I don't know, the set of text sequences as input, and you want to produce a sequence of images as output. Okay? Also, in everything that I will present today, I will only consider what we call time index signal, so where I will have a time dimension, or something that we can interpret as a time dimension. It could be, for example, the position in a piece of in a sentence in text, or it could be the position of the frame in a video. But what we'll see generalized to more dimensions, if you want, or to things that are not really time index signals. Okay, so let's say we want to solve one of these problems. The big problem with sequence-to-sequence problems, or every time you have to deal with a sequence, is that you don't know in advance what will be the length of the input sequence, or what will be even the length of the output sequence. So how do you deal with that? So if we take, generally speaking, the problem of sequence-to-sequence problem, the historical approach has been very simple. You divide the problem in two parts. So you have some input sequence on the left. You feed it to a first neural network, an encoder neural network that takes the entire sequence of some size and then produce an intermediate state as output, only one, okay, which supposedly is a good representation of the input sequence. And then from that fixed size vector only, then produce a sequence of tokens as output, and does that through a second neural network, which we call a decoder. Okay? So, for example, this would be the case of a encoder-decoder architecture based on a recurrent neural network, in which on the left you have the encoder part, so you have a neural network that you apply repeatedly to the elements of the sequence. Okay. And when you arrive to the end of the sequence, so EOS means end of sequence, so there is a symbol which marks the end of the sequence. Then you use the internal state representation of the recurrent neural network as the representation of the input sequence, so of the sequence they are watching, dot, and then end of sentence. And from this final representation, what you do is that you run another recurrent neural network, the decoder, getting as input at every step the representation that you've built through the encoder, along with the previous elements that have been generated by the decoder. Okay, so first you generate IL, and then you generate. So you have as input the beginning of the sentence that generates a first word, let's say IL, and then you do a next iteration through your recurrent neural network, taking as input the previous state of the recurrent neural network together with IL, and then produce the next word, and then you keep running this recurrent architecture. Yes?
So the output here is also received as a single dot vector and then decompressed into a sequence?
Yes, exactly. So you see that you only run over the input sequence once, that produces a fixed size vector. Okay, and then it's always the same vector that you feed as input at every step of the recurrent neural network. Okay, so let's take an example, and please pay attention, okay? And this is just to show you how this architecture would work and also to show you the limitations. Let's say we want to translate a sentence from English to French, okay? And this is the sentence. Or rather, oh, no. Oh. Okay, so read the sentence. Okay, you've read the sentence. Now translate it to French. The simple English sentence, give me the French translation. So, what was the sentence? Yes? Okay. So this is not even how this architecture would work. This architecture would be even more silly. What would happen is that if you run the first encoder as a recurrent neural network that takes the word, the element, the tokens one by one, what would happen is that as you read, you are building a representation of the input. So what would effectively happen through the encoder is not even that. Would be something like this. So you read the first token, then that's it, you have read it. Okay, this is what the encoder would do. If you implement it as a recurrent neural network, that would process these elements one by one. Okay, and then now you have some representation of that sentence in your mind. And what you have to do now is to run the decoder neural network, which will produce the translation one token after the other. Okay? And in this case, you could produce as an output, l'animal n'a pas traversé la rue car il était trop fatigué. Okay? So what are the limitations of this architecture? So first one, I mean, from this experiment is that only one of you could produce the translation. So why couldn't you produce it? Yeah. Yeah, so when you produce the translation, certainly, so what you mean is that I mean, that's not entirely correct, actually. Because when we produce the output tokens one by one, you see that the previous tokens that you have already generated, they are used, you have arrows connecting the next computation. So you take into account what you have already generated. So do you think this approach would work if I give you an entire page to translate? Or an entire book to translate? So the big issue is that we are taking as an input some sequence of size t, okay, which effectively means you would have a big tensor of size t times some number of channels that we use to represent each token. Okay, and we are trying to compress that to a fixed size vector, let's call it z, where this thing is of fixed dimension. Okay, D is set once and for all when you design the architecture. So regardless of the size t of the sequence, you will have to compress this entire thing into d numbers. Okay, and so of course there is only so much you can compress and store in these d elements. Okay, the other issue with this architecture is that it assumes that implicitly that this internal representation that we build and that we get as the output of the encoder will carry enough information to produce the entire translation. Okay? And so that's something which can work for short sequences, but as you will make the sequences larger and larger, that will become more and more difficult. Okay? So now what we'll see is a way to go around this problem by avoiding to compress or store the information about the entire input sequence in one vector. But instead, what we try to do is that when we generate the output elements, the output tokens, we'll basically dynamically, or we'll try to dynamically determine what are the input elements which are important to produce the next tokens. Okay? Okay, and the mechanism that we'll see for that is what we call Badano attention, or just attention. So Badano is the name of the author, of the researcher who proposed this mechanism. And it's based on a simple idea. So if you stare at something, and if you focus your attention on something, like if you look at me or if you look at the screen, you will see me very clearly, or you will see the screen very clearly. But if at the same time you wonder, okay, what's actually around me or around the screen, then it will be blurry. Okay, and that's something we do. I mean, that's very natural for us to do, but that's actually a very powerful mechanism, because if we could see everything with very accurate precision, then our brain would be overwhelmed with too much information. Okay? There is really an advantage of being able to focus your attention and basically the information that you receive to the next layers of your brain. And so, for example, if I give you, if I show you this list of things, so a newspaper, a pile of sheets, a red cup of coffee, this notebook or this book, your attention supposedly will be attracted to the red cup. Why is that? Because it's a bit different from the others. Okay, because these things looks interesting or a bit surprising with respect to the others. Okay. On the other hand, and that's something you would do again very naturally without any attention. However, if you know that you are looking for something, or if you know that you want to solve a task, let's say you want to read something, or you want to read a book, then your attention, now that you have a goal, okay, your attention will not be directed any longer to the cup of coffee, but maybe rather to the book. Okay? And that's exactly the mechanism that we'll try to implement. So if we have some intent, then we'll try to focus the attention of the neural network only on the input elements that are relevant with respect to this intent. Okay? But of course, we may also consider other elements, like the cup of coffee, because they are interesting by themselves. And it will be a trade-off between these two things. Okay, so abstractly, what we'll consider today is that we have a query, what I will call a query, which is your intent. Okay, what do you want to do? What is the task that you want to solve? And we'll use this query to basically tell us, among a set of values, which one you should consider, which one you should use for your processing. Okay? And the way we will do that is by assuming that each of these values, okay, they are associated to keys, okay, which represent the properties of these tokens. And the attention mechanism that we'll have in the middle would be a mechanism that will basically tell us how similar are the queries to the keys. And then given these similarity scores, will tell us, okay, if, for example, this first key is very similar to the query, then that means you should use the value associated to the first key. And on the other hand, if the second key is very dissimilar for the query, then you should not take into account the second value. Okay? And finally, we'll have a mechanism from this set of values to produce some output. Okay? So basically, this mechanism will give us a way, given a set of sensory inputs, like the entire image, okay, which we could see with high precision. The attention mechanism that we'll implement will restrict this set of inputs to only a subset of the available information. Okay? Okay. And so if we go back to our example with the English to French translation problem, what we'll have now is that as we produce the output tokens, what we'll do, or what this mechanism will allow us to do, is to attend to only use or only look at the information which is relevant for producing the next output token. So it will become clear if I go over this example again. Okay, so now with the attention mechanism, the input sequence will not disappear. Okay, so you will be able to look at it when you produce the output sequence. So if this is the input, now what would be the output? So how would you start the translation? Certainly, would you look at the entire sentence? Maybe, but on what part would you focus your attention? On this part, or maybe on this part? On the beginning, okay? Because you know that in English and French, I mean, the order of the words is more or less the same. If we were instead, for example, translating Dutch to French, then there are words that are at the very end of the sentence that you should put back at the beginning when you translate back to French. Okay? But that's not the case for English to French. So what would be the translation? Okay. So we have, basically, when you do that, we know that we should look at this part, and this other part is not really important, whatever that is. Okay, and once we have produced these words, okay, our intent changes a bit, okay, because we know that this part has already been translated, so we can go on and move on to produce the next words, the next token. What should it be? Yeah, so certainly we'll have to look at that. And how will we translate that? N'a pas traversé. Yes. Then. Là. Parce que il. How do you know that it should be il and not elle? Because in English it's it. But how do you know that it is the animal? Okay, but how do you determine that? Like, let me do one change, and you will see that you should not have translated it with il. The animal didn't cross the street because it was too wide. What is it now? Why? It's correct, but why? Okay, so that means when you translate it, you're actually attending to many words. Okay? You have to relate the animal, it, wide, street, and you do that very naturally. Okay? But you need to take into account all these pieces to make a correct translation. Okay? Also, when you translate because in French parce que, and you know that you should that the next word will be il, that should not be que, it should be q with an apostrophe. Okay? So that means you need also to anticipate and look not only at because, but also at the next words. Okay? Trop fatigué for the original sentence. And in elle était okay, so this example is also a good example of things that wouldn't work with the regular encoder vector decoder architecture, because these sentences, they are really almost the same. They are only different from one word, but the resulting translation is that it's quite different. Okay, but supposedly, if this sentence is encoded by a first recurrent neural network into a vector, first with the word tired and then the word wide, the resulting vectors would be very similar. Okay, and that means the output sequence, I mean, the job of the decoder would be quite difficult because it should be able to determine, okay, I'm in one of these two cases, and from this very slight difference, I should produce the correct translation. Okay, do you have questions so far? So this was just to give you an intuition. Now we'll see how to actually implement that. No questions? Okay. So the architecture that we'll first see is this one, which was proposed in the context of machine translation. And it's really an equivalent of this encoder vector decoder architecture, but what we will do differently is to replace the middle vector by an attention mechanism. Okay, so we'll still have a first recurrent neural network taking as input a sequence of tokens. But what will be different now is that when we run the decoder neural network, instead of just passing the vector produced or some vector produced by the encoder, what we'll use instead is a vector which is recomputed at every step through this attention mechanism. Okay? All right, so the idea is first to run what we call a bidirectional recurrent neural network. So recurrent neural networks are not something we've seen yet, but I'm not focusing too much on that because it's not really used anymore in deep learning. I mean, not that much. But it's basically just a function, a small neural network that you run on itself. So what you will have is something like you have some function f, which is a neural network. And this function takes as input some input element, x, for example, xt, together with a previous state. Let's call it ht minus 1. And that produces a new state ht. Okay? And the trick is to say, okay, you will call this function iteratively on x. So you have this input sequence from 1 to t. And at every call, you consume the next token xt. And for the second argument, you pass as input the output of the previous call of the function. Okay? And there are different ways to implement this f function, but that's not too important. If you are curious, there is a lecture on my GitHub about that, but I've decided to remove it from the main course. But what you should just understand is that this recurrent neural network will produce another sequence of tokens, of vectors, when you run it on the sequence. Okay? And the sequence that it will build will be the sequence of HT representations. Okay? So you will have as input a sequence, then you run it through your recurrent neural network, and that produces a sequence of vectors and this sequence is of the same size as the input sequence. Okay? And what is done there is to run the recurrent neural network forward and backward. Okay, because you could flip all the elements in the sequence and then pass it through the same recurrent neural network that would produce another output sequence, which would not be necessarily the flipped version of that sequence of vectors. Okay? That's what we call a bidirectional recurrent neural network. It's just basically two RNNs, one operating forward, the other operating backward over the input sequence. Okay? But at the end, that produces just a vector. When you concatenate these two forward-backward vectors into a bigger vectors, that produce a new vector representation, hj, for each input token xj. Okay? And then the idea, okay, so you compute this sequence 1, so it's as if you were reading basically the sequence to produce some new representation of its tokens. Okay? And now from this representation of this new representation of the tokens, what is proposed is to compute a new process Si, okay, just a variable, a vector, which will look at a weighted average of the Hj elements, okay, where the weights in this weighted average will be a function of the data, will be a function of the signal. Okay, so that will become clear when I run the example, but let me go to the end first. So let's assume that we have already generated some output elements from 1 to I minus 1, and we have already produced this S variable from 1 to I minus 1. What will be done next is to compute first an attention vector, which will basically use the current context, Si minus 1. Then we'll evaluate how this context is similar to each token in the input. And we do this comparison using the Hj elements. And we say two things are similar through an attention scoring function A, which we'll talk about later. And then we pass these scores to a softmax function. Okay, so you will have, for example, S vectors that are well aligned with the Hj, for which the score will be high. Others will not be aligned, the score will be smaller. And if you pass everything through a softmax, then you will get a vector of proportions, which you can interpret as how much you should use the corresponding vector. Okay, and that will give you the alpha ij values, the weights. And then we'll say that the context for producing the next token is just now a weighted average of the input tokens, the Hj input tokens, but where the weights in this weighted average have been computed through this mechanism. And once we have that, once we've built the context, then what they do in the architecture is to say, okay, the next Si will be computed from some f function, which is also a recurrent neural network, taking as input the previous context, taking as input the previous token which was generated at the previous step, together with the new context, Ci. Okay? And once you have this new process Si, then we eventually generate the next token, Yi, by saying that, okay, this G function will give us now a probability distribution over the next token. Okay, so that will take as input the context, the current Si value, the previous tokens, the token which was produced at the previous step. We instantiate this probability distribution and we sample a next token, Yi. Okay? So let's just do that step by step. Okay, so let's say we have an input sequence, xi, x2, x3, up to xt. Okay, each of these variables correspond to vectors of size c, so they are the tokens of the sequence. And the very first step in this mechanism is to pass this sequence to a recurrent neural network, okay, which basically will just take the entire input sequence as input, okay, and will produce as output a new representation of each token. So here we'll have H1, H2, H3, up to HT. Okay, let's say now that we have already generated a first output token and even a second one. So that means when I run this sequence of instructions, I've also computed S1 and S2. Okay, so the first step is to compute the alpha ij elements. Okay, so for us, that will, so now if we are there, we are at I equals 3. Okay, so I equal 1, I equal 2, I equals to 3. So we'll compute the alpha ij, 3, 1, alpha 3, 2, alpha 3, 3, alpha 3, t. Okay? And the computation of one of these alpha is something that you do by just comparing, in this case, for example, if we take this one, this is computed from S2 and from H3. Okay? Now, from all these weights, now we compute the context. So Ci, which in this case would be C3. And the way we do that is just by saying that C3 is a weighted average of the edge elements. Okay? But where the weights are given by the alphas. Okay? So maybe we'll have a large weight for this one. We'll have a big influence. Maybe this one will be small. Maybe this one will be almost 0. And maybe this one will be large as well, I don't know. Okay? But at the end, it's just a weighted average, where the width of the arrows there correspond to the amplitude of the weights. Once we have C3, next step is to recompute S, so S3. And we do that as a function of Si minus 1, so this one, of Yi minus 1, this one, and of the context, of course, C3. And finally, once we have S, we generate the next token, Y3, and we do that conditionally on the previous one, conditionally on S, and conditionally on the context. And then you iterate like this, and you stop, either when you arrive to a sequence of some fixed size, t or some other target length, or, and which is more common when it comes to text sentences, when you generate a token y, which correspond, for example, to the end of a sentence. Okay, and so what you should understand now is that basically to produce the next token, through this mechanism, you will look at only a subset of the input elements. Okay, and this selection mechanism is really done through the attention weights. Okay, so in this example, for example, the first and the last will have a strong influence. It's as if you were not looking at all the others. Okay, to produce the next token. Exactly as we did when we translated this piece of text. We're only looking at a few words, and as if we were discarding all the others in the sentence. Okay, so if you take the original paper about this attention mechanism, you will see that indeed it was used to build a machine translation system to go from English to French. And what they show in this paper are these maps, which correspond to the attention weights at every step of the generation. And so above you have the input sequence, and below you have the output sequence. So in English and in French, in English there and in French. And so what you see is that it's mostly diagonal, because in English and French, the words are usually ordered in the same way. You will usually preserve most of the ordering. And so to translate, so the agreement on the European Economic Area was signed in August 92. Well, since you know this similarity regarding the ordering, it's not surprising to see that, okay, when it comes to the weights that are being learned, by the way, by the neural network, we never tell to the neural network that there is this ordering between, which is maintained across the languages, but it discovers this regularity that to translate you should, to produce the first token element, you should focus on okay, to produce L, and then to produce the next token, you should attend on the second element, agreement, to produce accord, and so on and so forth. What you see, however, is this part, so where the diagonal is flipped, okay? But this happens when the system has to translate European Economic Area, which in French would be translated by flipping the ordering of the word, where we would first translate area, zone économique européenne. Okay? So it produces something which really makes sense. You see that sometimes you need to the system needs to attend to several words at once. When like was signed is translated to a été signé, where you need to go from 2 words, in this case to 3 words in the output sequence. Okay? Questions on this? Okay, then I propose that we take a short break of, let's say, 10 minutes. We resume at 9:35, and then we continue with the attention layers. Okay, we'll continue. So, do you have any questions so far? Okay. If you have, please just feel free to interrupt, because what we'll do next is to abstract away this attention mechanism into an attention layer, and then we'll be composing these things in a much, much bigger neural network. So if you are lost already, just tell me, because otherwise you will keep being lost after. All right. So the next part of today's lectures is to basically extract out this attention mechanism that we saw in this encoder attention decoder architecture for machine translation into a generic layer, okay, which would take as input a set of tokens and would produce as output a new set of tokens, but with a new representations for each of them. Okay? And a very simple way to understand that is that this attention mechanism, and it's really not incorrect to think about them in this way, is that they are just a glorified weighted average of the tokens. They produce a new representation of the tokens as some weighted average of the input tokens. Okay? It's nothing more than that, really. Okay, but so let's see how this is formally defined. So we'll define from now on the attention mechanism in the following way, where we'll have 3 elements as input. So we'll assume that we have a context or query vector Q. Okay. And you will see later how these inputs really materialize to something that we are more familiar with. But let's assume that for now we have some query input vector Q, which is just a vector of dimension q, that we have also, together with q, two other elements, a key tensor and a value tensor, where these key and value tensors, they share the same number of elements, the same number of rows, m, but the keys, they are defined over k-dimensional vectors and the values over v-dimensional vectors. Okay? And then we'll say simply that, starting from these three inputs, that an attention layer computes an output y of the same dimension as the of the same length as the length of a value, so v. So it will produce a vector of size v, and we'll say that y is the sum of the softmax values evaluated at some attention between the query and the key elements times the values. So what does that mean? It means that we'll have a scalar attention scoring function A, which will take as input first a query and then second a key. So in this case, ki corresponds to one of the m rows in key. Okay, so we evaluate this attention score for each key for the same query q. Yes? So you just assume that we have that. Just assume that, for example, we have a database or a big dictionary of key and values. Okay? And you have a query, you are looking for something. And all of these elements are vectors. Okay? Okay, so what I was saying is that, so you evaluate the attention score for every key in your database, every key in your key tensor with respect to q. That gives you all these attention scores, so m of them. You softmax these values, okay? So that produces now a vector of weights, which are all positive and smaller than 1, and when you sum them, you get a value of 1, okay? And then you say y is this sum of weights times the values associated to the keys. So this sum of softmax of v is just a weighted mean, where the weights are given by the softmax elements, and you do a mean over the values associated to the keys. That's it. So graphically, we would have something like this. We have a query vector, we have a set of keys, themselves as vectors. For each key in blue, we compute the attention score of the key with the query, there, and there, every time. That gives us a vector of scores. We compute the weights using a softmax activation functions. And then we'll say that, okay, the output is a sum over the values, but which you weights by the attention weights. Okay? So this is just a fancy diagram to say that we are doing a weighted mean. Okay? However, this is not a simple weighted mean because the weight, and that's really fundamental, because the weights there, they are function of the data. They are not fixed, they are not learned, they are a function of the keys and of the query. Okay. Okay, so how do we go a bit further? If we want really to implement this mechanism, the first thing we need to implement is this attention scoring function. So there are several possible choices. One of them is what we call additive attention. So, and which is something that you can use when the queries and the keys they do not share the same dimension. They are of different lengths. Then what you do is that you map the query Q to a vector by doing a linear projection through some matrix W transpose Q, which will project the query vector to a vector of size h. Okay, sorry. to a vector of size h. So you have the query vector, you project it by multiplying it by this matrix, and that will give you a vector of size h. You do the same for the keys. You map them to h-dimensional vectors. And now that both the key and the query are h-dimensional vectors, you can sum them. So that's what you do in additive attention. You sum them. That gives you a new vector of size h. And then finally, you have a third vector, W transpose V, which in this case is a learnable parameter, which you multiply with the output of the tanh activation of the sum of the two projections. Okay? And that dot product will give you a number which corresponds to the attention score between the key and the query. In most architectures today, we don't do additive attention, we do something else. We do scale.product attention, where we'll assume that the keys and the queries, they are already vectors of the same size. Okay? And since we have vectors of the same size, yes? Of V? It's a scalar. It gives you a number. Right? So that's a good question. So, but then that's something you should always do, and which you necessarily would have to do if you were to implement this. So vector times a matrix like this will give you a vector. This will give you a vector. So you have two vectors of the same size. You sum them, that gives you a vector of size h. You pass this vector through for example, through this activation function like the hyperbolic tangent, that gives you a vector of the same size, h. And now you multiply this vector with WT V transpose, which is a vector of size h. So you are doing a dot product of two vectors of the same size. That gives you a scalar. Okay? And if you were doing that in batch directly over the big K matrix, that would give you a vector of attention scores. Okay, so what I was saying is that if we know that the queries and the keys have the same length, then we can do something simpler. We can just implement use as a similarity mechanism for the scoring function the dot product itself. Okay, where we would say that the attention score for Q and K is given by their dot product. Okay, which makes sense. And the only thing that changes from a regular dot product is that we divide by the square root of D, where D is the dimension. So in this case, the length, the number of tokens that you have. And the reason we are doing that is because when we'll train these neural networks, we want them to behave the same regardless of the length, regardless of the number of tokens that you have. And so in this case, we would be normalizing in a sense by the number of tokens. And so the activation values, the attention values would be more or less on the same range regardless of the value of t. Yeah.
How do we know that Q and K will have the same size?
That's a choice that you make.
But in general,
But you will see that these attention layers will be buried in a bigger architecture where we will have designed this architecture such that the query and the keys will be of the same length, and even the values later on. Okay, so let's say this is now the attention scoring function that we consider. Then this can be rewritten in terms of matrix and vector operations to produce the output of the attention layer itself, where we can rewrite the output of the layer of the attention layer, so y, as we first compute the product of let's say we have n queries, not just one now, but several of them at once. We have m keys and m values associated to the keys. We can compute the output of the attention layer, which will be another matrix, y, where we have as many elements as we have elements in the query matrix, so n. Okay, so this entire thing is a matrix of size n, and we'll have as many columns, as many elements per token as we have for the values, so v. Okay. And then we'd say that, okay, we can rewrite this as the softmax of the product of the Q matrix with the K transpose matrix divided by the square root of D, because we use scale.product attention. We softmax this matrix row-wise, and then we multiply the resulting attention matrix with the value matrix, and that produces the output matrix. Okay. So I can jump maybe there directly. So let's say we have a query matrix like this, which is made of 10 elements, each described by 5 features. Okay. So we have 10 tokens represented as 5-dimensional vectors. Then we have queries. We have, you see that we have then we have keys. We have 8 of them, but each of these keys is represented by also a 5-dimensional vector. When we do the product Q times K transposed, we are building now this bigger matrix, which will have as many rows as we have queries and as many columns as we have keys. And each entry in this matrix will correspond to how similar, for example, if we take this one, how similar is this row, how similar is this query from, this was this one, from how similar is this row with, to this key. Okay, so each entry is just a similarity score between queries and keys. Okay, and similarity is just defined as a dot product. So, for example, if you take this query and this key, they look really the same. They are very similar, and we expect the similarity score to basically be large in this case, which will happen in this case if we use the dot product to compute these similarities. Okay. However, for example, if we compare this query with this key, they don't look the same at all. And indeed, when you look at the value there, it's close to 0. Okay, because the dot product is also close to 0. Okay? Okay, so we have this matrix. Then next step is to softmax this matrix row-wise. So you take each row one by one, and you softmax the vectors. Okay, so you take this vector, you pass it through a softmax, that gives you this. You take this vector, you pass it through a softmax, that gives you that, and so on and so forth. Okay, so now each row is, you can really interpret that as a vector of weights, positive and summing to 1. And then finally, what we'll do is to say that the output of the attention layer, so the output y, is a matrix where you have as many elements, as many rows as you had queries. Okay? And you have as many columns as we have columns representing each value. So in this case, if we have values represented by 3-dimensional vectors, okay, we'll have for the output also 3-dimensional vectors for each input token. Okay, and then we are just saying, for example, this first output vector is what? It's just the weighted mean. So if you take the first element of this output vector, it's computed as the weighted mean of these values, or rather of the first element of the values, where the weights are given by this row. Okay? Simple as that. And so if we take, for example, this one, you see that it's mostly selecting the first value, or key, okay? All the attention weights are close to 0, which means that when you do the weighted mean of this with V, you will only basically select the first row of V, and indeed this is what you see reported in the output of the Y matrix. Okay, this row is the same as here, more or less. Questions? Okay, so what you should understand is that we start from n tokens, and we produce n tokens as output, and what changes in between are the representations of the tokens. Okay, and we compute the new representation by just computing a weighted mean of the current representation in V of the tokens. Okay? Okay, then the question is, but this query key and values, where do they come from? So what we do usually is just to derive them from some fixed set of inputs. So let's assume that we have two sets with two input sequences, x, which would be made of n elements of size x, and x prime, which will be made of m elements of size x prime. Okay? Then we'll say that Q is a linear projection of the x elements, okay, where we multiply this tensor with a matrix to obtain now a d-dimensional representation of the n input tokens. And for the key and values, we will derive them from the other input matrix, x prime, where we'll do something similar. We say that we start with x prime dimensional vectors, but we just project them to a common vector space of size d through first a matrix projecting the keys, and a matrix projecting the values. Okay? And then if we want to simplify this even further, what we can do is to say that x and x prime, they are the same. They are the same elements. Okay, so when the queries, the keys, and the values are derived from the same set of input tokens, you obtain something that we call a self-attention layer. Okay? Where you'll focus your attention not on something external, but on the input itself. Okay, and really now, you can view the self-attention layer as just a regular layer, which takes as input tokens, represented as a matrix X, and produces as output another matrix with the same number of elements. Maybe you can change the number of dimensions, but you could keep it. And it's really something that goes from a tensor to a tensor. Okay, exactly like a fully connected layer goes from vectors to vectors. Okay? Questions on this? Okay, one interesting thing that we can do that now that we've defined the self-attention layer is to try to better understand how this layer relates to what we have seen before. And what we have seen before are the fully connected layers, the convolutional layers, and there is also this other thing which you see in the slide, which correspond to the recurrent layers, which I will skip. Okay. But actually, what I want to stress today is that the self-attention layer is very, very close to a convolutional layer and also to a fully connected layer. We already knew that convolutions and fully connected layers are very related. You can express a convolution layer as a fully connected layer. And what I will show you now is that the self-attention layer is something very close also to a fully connected layer, but strictly more powerful nonetheless. Okay. Okay, so let's assume that we have some input matrix X, okay, which is made of n elements or n tokens, and each of them is described by a number of features. Okay, the very first step is to go if we were to feed this X through a self-attention layer, would be to rebuild these Q, K, and V matrices. Okay, which would happen by multiplying X with another matrix like this one to produce. So that would be so this one would be W, for example, for the keys, WK transposed. And this gives us, so maybe you should wait a bit before drawing what I do. This will give us the key matrix or the key transpose matrix, okay, which we compute from this. We'll have the query matrix, which we derive in a way very similar. We start from the same X, the same as this one, but we multiply it by another matrix, in this case W T transpose Q. Okay. Then we do the product of these two matrices. That gives us the attention matrix after doing the softmax. Okay. And then to produce the output, we'll be multiplying this matrix by a V matrix, which we have obtained also in a way similar to the keys and the queries. Now we start from the same set of tokens, X, multiply that by W transpose V. And that gives us this, and finally we obtain Y. Okay? Okay, and what matters really is for you to understand that to compute Y, we are multiplying a matrix with this to obtain this output. Okay? And if we just consider one column of V, we are multiplying a matrix with a vector, a column vector, to produce another column vector. Right? Now, what do we do in a fully connected layer? So in a fully connected layer, where we say that we compute, for example, H as W transpose times X, okay, we obtain a vector from the product of a matrix with a vector. Okay, so if we draw this, we have W times a vector X, and that produces H. Okay. Now, if you say that you have several vectors and you stack them along the second dimension, you would have something larger there, and that would produce, so you would have, let's say, C vectors, and that would produce, if you just apply the same linear layer to each of them, you would have now C output vector after the linear layer. Okay, and what I'm saying is that this is very similar to that. Okay, where here we have a matrix that produces a matrix. Okay, both of them are, in a sense, I mean, they are really linear operations. But there is really one and fundamental difference, is that A, this matrix, is a function of the data. It's a function of X. Okay, because we have derived A from the product of the keys and the queries, which are themselves functions of the data. So it's as if a self-attention layer was a fully connected layer, where the weights are not trained and set once and for all, where the weights will change dynamically as a function of the data. Does that make sense? Well, we can also reason about the structure of the matrix. So in a fully connected layer, this matrix will be dense. Okay. In the attention layer, it's dense also, but it has some structure because we derive it from by doing a softmax on the rows. Okay, so the interpretation is slightly different. And what is also true is that when you compute the entries there, so if you remember, we do so we compute that as the dot product of the weights and the queries, okay, of the queries and the keys, and yeah. So what will happen is that the same, indirectly the same, so the parameters here and there, which we use to produce the keys and the queries, they will also be shared in a sense to compute the entries of the A matrix. Okay, because each X vector will be projected using the same projection. Okay, and so the entries will also share some parameters. And this is similar to what we have seen when we talked about convolutions. We've said a convolution can be expressed as a matrix times a vector, but, and you would have this diagonal matrix, if you remember, this, where on the diagonal you would have the kernel. Okay, but what makes a convolution a bit special is that these weights, they are shared. Okay, you reuse them for the inside elements. And that's indirectly the same which will also happen in the attention layer, because the keys and the queries are obtained from the data using the same projections. These weights are shared, okay, meaning that these entries also will be computed from shared weights. Okay, now if I want to comment more specifically on this slide, first we can look at to what inputs and how inputs and outputs are connected. If you take a regular fully connected layer, all the inputs are connected to all the outputs. Yes? They are learned. So these three small matrices, they are learnable parameters, okay, which we'll learn by just doing the regular optimization process. Yeah. Yeah, so really the parameters there, it's not A, as you would have in a regular fully connected layer. The learnable parameters, they are there. Okay, from these three parameters, everything else follows. While for the fully connected, this entire thing would be learned. Okay, so I was saying, what about the connections between the inputs and the outputs? If you take a regular fully connected layer, all the inputs are used to compute all the outputs. If you take a CNN, we build the convolution by trying to exploit this locality assumption, where only a subset of the inputs would be used to compute an element in the output. With a self-attention layer, we have something a bit in between. It's, mathematically speaking, fully connected also, because when you compute a token, you do it as a weighted average of all the other tokens. But because you compute the weights using the softmax activation function, usually only a few of the weights will be significantly larger than 0, and so only a subset will effectively contribute to the final representation. Also, what is interesting is to wonder about what is the length of a path connecting two nodes, an input and an output. So if you take a self-attention layer or regular fully connected layer, any input can have a direct effect on any output. Okay. If you take a convolutional layer, you will not have this. Only a subset of the inputs will have an effect on one element or a few elements of the output. For the effect of an input element to propagate to any other output element, you need to stack several layers. Okay? For example, you need to stack several convolutional layers, and that will increase the receptive field, as we have seen, and you can accelerate that if you add pooling layers. Okay? So that means it may take some time in this architecture for the information to propagate, while in a self-attention layer, if the connection needs to be direct, this is allowed by the architecture. Okay? The layer itself has the capacity to make direct connections directly between any input and any output. And if you take so in the case of the CNN, that will take, if you consider the pooling layers, that will take a logarithmic number of convolutions to connect any input to any output. With a self-attention layer or fully connected layer, you just need one layer. And if you consider the recurrent neural network, if you want to connect any input to any outputs, you will need to, in this case, at worst, a linear number of activations, a linear number of activations. Okay. In terms of complexity, these layers, they are not equal. If you take the self-attention layer that we have seen, the complexity per layer is quadratic in the size of the sequence, and linear in the dimension d of each token. Or yeah, maybe just not to confuse you, this is d, this is d. If you take a convolutional layer, you will have something which is usually cheaper, where you have a cost which is not quadratic in the size of the inputs. So if you have large input sets, it's only linear in the size. If you have a large input set for a self-attention layer, it becomes quadratic, and that can become an issue. So can you tell me why we have this quadratic cost for the self-attention? Yeah. Which one? Between the keys and the queries, yeah. So we have the quadratic cost because we have to instantiate this big matrix, which has a size of n by n. As simple as that. But that may look like something not too important, but as soon as you are dealing with sequences of a few thousands of elements, that becomes very quickly an issue. All right. So this is an example that would illustrate the behavior of an attention mechanism in which the task of this problem is it's a sequence-to-sequence problem where you have a sequence as input and you have another sequence as output, one-dimensional sequence of numbers. And it's composed of two patterns, triangles and rectangles. And the goal here is to produce as output a sequence in which the eighth of the triangle would be the average eighth of the triangles in the input. And similarly for the rectangles, the eighth of the output rectangle should be the average eighth of the input rectangles. Okay? So that means if you want to do that, the neural network should be able to recognize the shapes, and then also to associate the shapes together, and then to compute a weighted mean, to derive the eighths, from which then it can generate the output. So if you do that with regular layers first, and then with self-attention layer, we'll see that one approach works very well. If you do it with these attention layers, then you can basically solve the task. If you train an MLP to do that, or a recurrent neural network, that will not work so well, and you will not be able to solve the task. Okay? And why? Because really, in order to do that precisely, you need to select what is important from the inputs to produce, then to reason, and then to produce the appropriate output. Okay? If you consider another problem where instead of producing the average eighth of the input triangles or the average eighth of the input rectangles, you say that in the output sequence you should reproduce the same shapes, but where the eighths for the two first shapes will be the average eighth of the two first elements, of the two leftmost elements. And similarly, the eighth of the remaining two elements should be the average eighth of the two elements on the right. Then what do you think will happen? So we use the same network with self-attention layers, and we try to solve this problem of generating a new output sequence given the input sequence. Okay, that's correct. So if you pay attention to what is going on in an attention layer, there is no information about positions. We never used ever the information about the position of the token. That does not even exist in an attention layer. While, for example, in a convolution, you exploit this neighborhood. There is some kind of notion of neighborhood between pixels, or in a fully connected layer, you have a position that you associate to each element. Here we don't have that. Okay? And precisely what will happen is that the performance of a self-attention layer trying to solve this task will be quite poor because it can't reason about the relative positions of these things, of the tokens. And indeed, mathematically, what would happen is that we can show that the self-attention layer is permutation invariant. If you permute the token, you will get the same output. Okay, why? Because if you take a weighted average, you permute the weighted elements, you still get the same answer. Okay? So that's something that will also happen in a self-attention layer. If you permute by some permutation sigma the keys and the values, you will get the same answer as if you didn't permute these elements. Okay? Which in this case is a problem because we will be deriving the keys and the values from these tokens. Okay, so if I'm telling you that if we permute them, the answer will not change, there is then no way for the network to understand what is left from what is right. Okay, so how could we solve this problem? Yeah, so you had a feature about the position in the vectors of the tokens. Okay? And if you do that, if you add this positional information, and there are various ways to do that, but that's not important, what you see is that eventually the network understands the task and is now able to solve it. Okay? Questions? Okay, then let's do a next break then before we dive into the transformers. And we'll resume again in 10 minutes, more or less. Okay. So now we'll continue. So if we summarize what we've seen basically one new kind of layer, the self-attention layer, or the version also where you can have cross-attention with two different inputs, n and x prime. What we'll do now is to build a bigger architecture around this new layer, which we call the transformer. Okay, so really this architecture has become something really fundamental in deep learning. It was first proposed by Vashwani and co-authors in 2017. And the goal was really to see if we could push this attention mechanisms further than what was already known with this cross-attention mechanism as used in the machine translation system. And the goal of that paper was to see if we could actually build an architecture of a neural network where self-attention layer would replace almost entirely regular convolutional or recurrent layers. Okay? And so what they propose is a transformer architecture, which will be a composition of several of these layers in several blocks. And initially, this transformer was designed for sequence-to-sequence translation task, so sequence-to-sequence synthesis. But actually, and this is what we'll see also today and later on in the course, you can recycle the same architecture for many other tasks, which you can express as a mapping between tokens from a set of tokens to the same set of tokens, but with a new representation. Okay, so it builds on what we have seen. It uses as an attention mechanism the scale.product attention, which is defined exactly as we have seen in the first part of the course today. So it's we assume that we have query keys and value matrices, and we compute the attention of the tree by doing the matrix product of Q and K transpose. We rescaled by the square root of the dimension of the vectors of the tokens. We softmax row-wise, and then we multiply the resulting attention matrix with the values to produce the output of the layer. Okay? But actually, in a block, in a transformer block, the idea is not to use only one self-attention layer, is to use them or to use several of them in parallel. Just like we built a regular layer as a parallel composition of logistic activation functions, or just like in a convolutions we are using several kernels in parallel, you can also have several of these self-attention layers in parallel. And if you do that, what you obtain is what we call a multi-head attention mechanism, which is just a concatenation of the output of several independent self-attention layers, where even if the notations are a bit heavy, it's quite simple to understand. You start from the same query keys and values, okay, but and then you direct them to a first attention layer. But the idea is instead of using the queries and the raw query keys and values, you project them with learnable parameters, and then you use the projections as input to the self-attention layers. Okay, so you would have a first projection through these fully connected layers of the queries, the keys, and the values, and then you pass the projected query keys and values to the a self-attention layer, and you would repeat that, but every time reusing other projections, which you would learn. And so, for example, there you would have a last self-attention layer, which is tied to its own projections. Then what we have is that each of these self-attention layers produce its new representation of the tokens. And then what we do to produce the output of the entire multi-head attention module is to concatenate along the dimension of the features of the tokens all these token representation produced by each self-attention module to produce the final output. Okay? So mathematically, if we assume that the keys, the queries, and the values all share the same dimension D, and typically, at least in the original transformer architecture, it was set to 64. And we assume that we have 8 parallel self-attention layers, which we call heads. So we have 8 heads. Then each HI will be the result of the projection of the query keys and values. This H will correspond to a matrix where the size is the number of tokens and the output, the dimension of each vector is 64 because we are taking weighted average of 64 dimensional vectors. Then we concatenate everything. If we have 8 heads, that means now the tokens are associated to 512 dimensional vectors, 8 times 64. And finally, there is also final projection to keep the dimensions small if we want, which would go back, for example, from 512 back to 64. Okay? So that's what we call a multi-head attention, which is just basically a layer of self-attentions. Okay? Then, in the transformer architecture, the original one, they proposed again an encoder-decoder architecture, where you have an encoder ingesting the input sequence, like in English, and then you have the decoder producing the output sequence, in French, for example. Now, the encoder will be made of a stack of 6 modules, where each module is composed of a multi-head attention submodule, exactly as in the previous slide, and also a per component one hidden layer or per token one hidden layer MLP with skip connections and normalizations. Okay, so you will stack several of those 6 times to produce the output of the encoder. Then you have the decoder, which is slightly more complicated, but almost the same, where you have also a stack of 6 modules. But now we are using mask self-attention because when we generate the output, we require the network only to attend to tokens that have already been generated and not to future tokens. That's just a mechanism which is implemented in this mask self-attention. And also, we will have 2 attention modules, one on the tokens that have already been generated, and one which will be a cross-attention in this case using the activation produced by the encoder for the keys and the values on one hand, and then using the values, the queries produced by the submodule below. So maybe a diagram will be easier to understand. So you have on the left the encoder network, on the right the decoder network, and the 2 of them together is what we call the transformer architecture. But so if we decompose that, we have 6 of these modules which we stack. We have 6 of these modules which we stack, so it becomes a quite large neural network. And each of these modules, if we take the encoder, it starts with the tokens which are embedded. So usually we start with characters or words which you have to associate to vectors, and we will do that through an embedding mechanism, which could be just a hash table, as simple as that, mapping characters or words to vectors. Okay. We add the information about the positions of the token in the sentence using positional encoding. And then comes the blocks, where first we'll have this multi-head attention module, which internally will have these parallel self-attention mechanisms. Then we have a skip connection. Okay, so that meaning we'll update the tokens by just keeping its current state, but maybe modifying it, but by what comes out of the multi-head self-attention module. There is also some normalization mechanism. And then there is what is known as a position-wise feed-forward neural network, just a small MLP that you apply in isolation to each token. Okay? That will transform the tokens into new tokens, will change the representations. Again, there are skip connections, normalizations, and you repeat this 6 times in the original architecture. And then to produce the output, so let's say we have already generated a few tokens, maybe the first few words. So we need to take that into account to generate the next one. So there will be the part below in the decoder will attend to these tokens which have been generated. And again, they are represented by vectors producing by an embedding layer together with the position. Then we have, again, a multi-head attention, but now a masked multi-head self-attention. We have similarly skip connections, normalizations, and it's there you see that we have a second attention module where now you have 2 arrows coming from the encoder and 1 arrow coming from below. So the 2 arrows there, they correspond to the keys and the queries produced by the encoder, okay, or key or queries produced by the encoder. And the arrow below correspond to the... No, sorry, I said something wrong. It's not the keys and the queries, it's the keys and the values. Okay, and the queries, they come from below, from the what you have generated so far. Okay, the queries give you the context of what you have already generated. And again, skip connections, normalization, the same kind of position-wise feed-forward neural network, again with skip connections, and finally a fully connected layer to produce the output token. Can you tell me, if you have understood well what you are doing, what should be the dimension of this final fully connected layer? So if we have this as an input again, okay, the first step, if you want to translate that to French, okay, the first step will be the embedding. So we'll transform, let's say we tokenize also, we split the sentence into tokens at the word level. So we would associate a vector to the, another vector to animal, another to, let's say, didn't, and another to cross. Okay? So we transform the input sequence to an input of vectors through the embedding. We add the positions. Everything passes through the encoder. And at the end, after the encoder, what you get, what do you get as output of the encoder? Sorry? No, not yet. That will be the output of the decoder. But not even that. The decoder will produce actually the tokens one by one. So the output, if you feed this set of tokens as input to the encoder, what you will get is something similar to what you get out of a self-attention layer. What you get is also a set of tokens. Okay? So basically, we've just changed the internal representation of a token after passing through the encoder. Okay, but we are still left with a sequence or a set of tokens. Okay, and now that we have this set of tokens, what we'll do is that we'll generate tokens for the output one by one. Okay, and we'll say that the encoder so this is for the input, and now the output. So for the output, you have to start with something, and usually we'll start with a special character which will indicate the beginning of the sentence, BOS. Or I will pass it rather there, BOS. This symbol or this token is also associated to a vector, okay, from the embedding layer. Okay, and now the task is, given this first empty token, generate the next one. But do that conditionally on this context. Okay, so we'll feed the first token as input there to the decoder. This token will be processed by first the mask multi-head the mask multi-head attention layer. Will produce a new vector for that token. Okay, and then we'll look at, okay, given this query token, or a query that I can derive from this token, and given keys and values that I can derive from this context in red, then produce a new representation of that token, and repeat that with several blocks until you arrive to a representation of the token for which you have to make a final prediction. And the final prediction is to guess the next word. So that means we have to go from a d-dimensional vector to a vector describing our choice among all possible next words. Okay? So this fully connected layer, the final one just at the very top, what should be its size? So the size of this projection, this final projection, should be as large as the size of your vocabulary, because you want to predict the next word. So it's a choice among all possible next words. Okay, so that final projection can be quite large, this one. Yeah, it will be in the tens of thousands of dimensions. And then once we have projected, once we have this vector, what do we do to produce the next token? So effectively, this whole thing will compute a probability distribution over the next word t, given words that you have already generated in the target sentence, and given the context x from 1 to L, let's say, that you have processed through the encoder. Okay? So this final layer will give me a vector of probability values for each possible next word. And then how do I generate that next token actually? Yeah. Yeah. So you could take you could pick as the next word the word which is the most likely. Or you could also just sample from this distribution randomly. And how do you think we train this architecture, at least in the case of translation? Do we know the next word? Or do we have data which would tell us a good next word is this? Yes, we can assume that we have pairs of, for example, at least in this case, of input sentences and output sentences in one language and in the other. So we know what should be a good next word. Okay? So how do we train this? If we have such a data set, what loss function would you use? Yeah. Yes, why the cross entropy? It's not like it is a classification problem. Okay? So this sentence to sentence problem, we can reduce it just to, if you decompose the output sequence as a sequence of small classification problem over each possible token, given what you have already generated. Each of these small problem is a classification problem, which we would train by minimizing a cross-entropy loss. Okay? Okay, so there you have another example of this process where, again, it's for translation, but now going from French to English, where you want to use this architecture to translate Je suis étudiant in French to something in English. And so you see all the steps. The sentence is split into words. It's tokenized into words. To each word, you associate a vector, in this case of 4 elements. You add the positions or positional information to these vectors, and then you pass these tokens to the encoder neural network, and so to each of these modules. And you see that the final output will be also 3 tokens, as many as you had in the inputs, but now the actual values will be different. Okay? But it's exactly as I was explaining. You start from a set of inputs, and you get just the same set of tokens, but with other values. And then, for the decoder, now we will create the tokens one by one by having the decoder using the previous tokens, if there is any already generated, and the keys and the values derived from these vectors computed by the decoder. The encoder, sorry. So let's say we run it once, then that produces a first word I, and then to predict the next, now we feed the first token or the first few tokens that we've already generated as inputs to the decoder. And so now, when the decoder processes this prefix that you've already generated, the representation that you compute of the token will change, of course, because depending on the context, the meaning of the tokens will change. But otherwise, the same mechanism. And again, we condition the generation of the next given the keys and the values generated before. Okay? So, yeah, that I can skip for now. And this is about the positional encoding. So there are several ways to encode the positions. So historically, researchers have used something like this, where you encode the position of a token within a sentence using a d-dimensional again vector, which will be basically some kind of decomposition of the position itself into some basis, in this case made of sinus and cosinus. But basically what you have to understand is that to each unique position, you associate a vector, which could be something like this, which is derived from these two formulas. Okay. But these days we are not using that really anymore. What we are just saying is that the positions T themselves are associated to vectors that we learn, and that's it. Okay. And then what do we do? That's something maybe I can comment now. If you consider that this positional encoding will receive as input the position of the token, let's say it's the third token, then you will retrieve the third vector as output of the positional encoding, representing the third position. And then, and that might be surprising, what you often do is just we take this vector, we sum it with the embedding vector. Okay, we don't concatenate, we really just add it on top of the embedding vectors, and then we proceed. Okay. Okay. This is yet another example of all this mechanism in the case of machine translation. So the original transformer was trained on this. And this is an example on the sentence I was using earlier. The animal didn't cross the street because it was too tired. You see that after bubbling through the encoder, what is interesting to notice is that if you look at the attention score between it and the other words, you will see that after traversing some of the modules, the meaning of it will be associated to animal and street, but mostly to animal. Okay, it knows that it has discovered that it should look at the two, okay, but mostly it's on the animal. And why does that happen is that actually you should see the self-attention mechanism as a way to reinforce the meaning of a token contextually on the others. So if you take, I don't have it. No. If you take this sentence, if you just read it once, or if you just have one pass of the encoder of the tokens, the meaning of it will be unclear. Okay, but you know, I mean, the network will discover that it relates to some other words by training, and it will relate certainly to animal and street and maybe tired. Okay, but then during the next pass through the second block, because of the context now, you know that, I mean, the network has the capacity to disambiguate the meaning of it given the context. And so, for example, if it uses the tired adjective, from that it can infer that it does not refer to street but to animal. Okay, so each pass you should, through a self-attention block, you should see that as a way to reinforce the meaning and to remove the disambiguities by using the context, the other tokens. Yes?
This is, it can do this because it has been trained to know that tired is more an adjective than animal.
So it's never explicitly trained to do that. The real training objective is just to guess the next word. That's it. But if you then inspect the attention matrix, for example, and you show it in this case for one row, so for one token with respect to the others, this is what you will see. Okay. And you see that for this other example, when you change the adjective to wide, then it mostly refers to street now, which is correct. Okay. Even though the neural network was never trained explicitly to do that, but this is just showing you that this self-attention mechanism is really using the context to reinforce the meaning of all these tokens with respect to the others. Okay. You have other kind of attention matrices if you're curious, but we obtain something very similar to what we had before with the Badano attention mechanisms. Okay, what we are doing now this day in 2025, and we've been doing that for some years now, is not exactly this architecture, but it's a simplification of this architecture where basically we remove the encoder entirely. We remove this one, and we only keep the mask multi-head attention and the position-wise feed-forward neural network. We keep the skip connections, we keep the normalization layers, and we just stack many of these modules. And that's what we call the decoder-only transformer. And that's basically what's driving everything if you use ChatGPT or other systems. They are all based on this architecture, decoder-only transformers. And how do we train them? Well, the nice thing about the decoder-only transformer is that the only thing you need are sentences or tokens. And you don't need to have pairs of inputs and outputs. And usually we train them to what we call obtain language models, in which the goal will be to obtain a model which will give us access to a probability distribution over the next words given previous words. Okay? And this is quite convenient because in this case we can use self-supervised learning. We can just take any piece of text and train from it. You take the prefix and then you try to guess the next word. That's it. You don't need to have pairs of English and French, for example. But this, of course, will only give you access to a language model which can reproduce the sentences on which you have trained on. Okay? But other than that, the architecture is very similar. It's made of the same blocks. And so, for example, if we feed, if this is the transformer decoder, and we start by a big, just this empty token beginning of sentence, then we do one pass through the decoder that will give us access to the probability distribution over the first word given an empty word, and from which we sample. So it could be I, and then we iterate, we feed back this I in the beginning of the sentence as an input sequence to the transformer decoder. We make a forward pass through everything, and that will give us access now to a probability distribution over the second word, given that the first word is I, and so on. And then we iterate like this repeatedly to produce the output sequence. Okay? Um, Okay, so this is a JavaScript demo of a decoder-only transformer, in which you can feed as input any sentence. For example, the animal didn't cross the street because it Okay, so you have there on the left the inputs, which are, so you have the sentence first, which is parsed into tokens at the word level. Then each word is associated to a vector of dimension, in this case 768. Maybe we can increase. Together with the token embedding, we add a position, which is just an encoding of really the position within the sentence. So the is at position 0, animal is at position 1, and so on and so forth. These are themselves vectors that we can learn or obtain from these positional encoding strategies. We add the two together, and we have now this representation for the tokens. Now, this is passed through a first block, which is made of skip connections, multi-head self-attention, skip connection, feed-forward neural network, and then that processes the output. So you have the residuals, which are shown there. You have the normalization. Then we enter inside the multi-head self-attention, which you see there. Okay. In this case, it would be made of 12 heads. So in parallel, we would have 12 of this self-attention module. So this would be the third, fourth, and so on. And you see that each of the vectors are mapped to 3 vectors, a query, a key, and a value vector, okay, which you see in blue, red, and green, from which then we derive first the attention matrix by multiplying the keys with the queries. Then we use this attention matrix together with the value vectors to produce the output. Okay, that produces new representation for each token, and we do that for each of the 12 heads. Then it concatenates everything to produce the output vector here. So you also see So we have the input values, the attention, and the output, which are computed as a weighted mean of the values. Then we have the MLP inside. Wait, multi-head self-attention, okay. Then we have a skip connection. And where is the MLP? Is there. Okay, where in the MLP, usually what we do is that we upscale the size of each vector by a factor of 4. So in this case, they would go from 700 dimensional to 3000 more or less dimensional vectors, 3072. So these are one hidden layer MLP, and then back to the original dimension, 700. Again, with the skip connections, and that produces the output of the first block. And then you repeat that for many blocks, a second, a third, a fourth, and so on. So in this case, that would be 12 of them. And finally, you would take the vector at the last position, which you project with this final fully connected layer to a big vector as long as the size of your vocabulary, okay? And each value would indicate how likely you think, or the transformer network thinks, that the next word should be this word. So in this case, if you look at the top 5, the first guess would be was, with a probability of 71%. or didn't with 10% probability, or add with 8% probability, and so on and so forth. And in this case, what they do in this demo is just to sample randomly from one of these 5 choices, of course proportionally to their probability. So in this case, it would have generated didn't, and then you add that word, you generate the token, and then if you generate again, then didn't becomes an input of the encoder. You do again an entire forward pass to this big thing up to the end, and now the next token is '(t), and then you keep generating like this. Okay, questions? Okay, so let me wrap up this part. So this architecture is really the architecture which is used now in many applications. Historically, this first architecture was used as a pre-training step, and then, so this was the case of GPT-1, the very first version of ChatGPT, so a few years ago, in 2018, before it was known to everyone. But really already you had this architecture which you see there, the self-attention, the normalization, the feed-forward normalization. You repeat that many times on tokens computed from the text and the position and their positions. And then the idea was just to have this big pre-trained neural networks which you train in a self-supervised way just on sentences that you find on the internet. And then you use this neural network to produce good representation of sentences to which you connect then specialized neural networks. For example, to do classification, entailment, to compare sentences, or to answer questions. Okay? That's not what we do anymore, really. We don't have this specific heads anymore. Now you have really general purpose architecture which just produce tokens, and if you can express your task as tokens, then usually it will be good to go without any further training of the neural network. What is really interesting, or has been quite interesting for the community, is how good these neural networks are. And so basically what we have noticed for a few years now, maybe now it has slowed down, but for a few years this was really the case, is that the longer you train these architectures, the better. So if you can scale to thousands or tens of thousands of GPUs, the better you will be. The larger the data set, so the more the tokens you have for training, the better. And so these are plots showing every time the test loss, first as a function of compute, and then as a function of the size of the training set. And the same for the number of parameters. The bigger you make these neural networks, the better. Okay, so that's maybe not very smart, and a bit brute force-like, but that's what has been working very well. Just make everything bigger, and you will get better results. And what is even more interesting, I would say, is that these bigger models, they are not necessarily less efficient than smaller models. And that's a bit counterintuitive, but this is shown in this plot, where you see that in terms of the test loss, and in terms of the same number of tokens that you process, if you compare the performance that you get between a very large model with billions of parameters or thousands of parameters, there is a huge difference in terms of the quality. So it's not because you are making the neural network bigger, or you could think that, okay, I have a small data set, therefore I will use a small model. That would be wrong, actually. And this is what this plot is showing. for a data set, a fixed size data set, the bigger model will be better. And you will reach also you will reach results which are better with fewer operations needed for training. Okay. And of course, an application of that are conversational agents. So really, ChatGPT and other systems, they are built on this decoder-only architecture. There is really not much more to it than that. And so that's what we'll try to implement actually next week. I will show you that we can rewrite and implement one of these decoder-only architecture from scratch, train it, and obtain something which produce things that start resembling sentences. And then if you plug that with bigger data set, more parameters, more compute, you can obtain something similar to ChatGPT. Okay? Questions? So, only 6 slides. So I will continue then. So I said at the beginning that these transformer architectures, now you were seeing them almost everywhere, and that's true. That has been true very quickly for everything related to language and text, but actually that's also true for other domains like images. So we've seen in the past 2 weeks that good architectures for dealing with images were convolutional neural networks. But actually, these transformer architectures, they are also very good at dealing with images. How is that possible? Let's say you think a transformer is something you could use on images. How would you proceed? So really the key when you want to use a transformer is to transform your problem into tokens. As soon as you have tokens, you are good to go and you can proceed with the transformer. So the trick to use transformer on images is to find a way to transform an image into tokens. And a very simple way to do that is to say an image okay, with this cat again. An image, from an image, I can extract tokens by considering, for example, small patches. Okay, and you will say that the content of one of these patches is a token. So you take the pixel content of one of these patches, you flatten it into a big vector, and you say, this is my token. And maybe you associate also to that vector a position, a vertical and horizontal position, because that's certainly useful to know where this content is in the image. And then you feed everything to the transformer network. If you do that, you get an architecture which is now very popular, which is called the VIT, the Vision Transformer, which is exactly doing that. You take an image, you divide it into small patches. Then this becomes your tokens. You feed them to the transformer architecture. So again, you have an embedding of these patches into vectors, and you add the positions. But other than that, you have the regular decoder-only architecture, which is made of multi-head attention, MLP, skip connections, normalizations. You repeat everything, and what you get as output are as many tokens as you had in the input, okay, but represented in a different way. And if you want, for example, to do that, to use that to classify an image, the trick is to say, in addition to the tokens representing the image, I will add a special token, which corresponds to a class token, just a special token. You will train jointly everything, so you will add this special token to the other tokens, you will feed everything, and then when you train, you will use the representation associated to this class token as an input to an MLP, a very short classifier, a very shallow classifier, and then you will classify the images. And then if you train, for example, such an architecture or a VIT architecture on images for which you know the class, okay, by doing this, then you will get usually very, very good results. No convolutions, no nothing, just you patch the image, you flatten everything, and then you use the attention mechanism, or basically the attention mechanism will learn to relate these patches as positions into things that mean something, or that can be useful at least for solving the task. Okay. Okay, and just like for text, where the decoder-only transformer usually are very good at learning representations that are useful to solve many tasks, you have the same thing for vision transformer. The representation that you learn from a VIT not only can be used for classification, but for many other things, like object detection, image generations, and all these tasks that we talked about last week can also be solved using a transformer. Yes? Yeah.
How can we choose the size of the image?
That's a fixed hyperparameter. Usually, for quite a while, it was done using 16 by 16 patches. But of course, this, you could use fewer pixels per patch, but then you would have more tokens. Or you could use larger patches, but you would have fewer tokens in this case. So it's a trade-off. Yeah. Better. Yeah. If you look at benchmarks, it's mostly variations of VITs. You have hybrid models combining convolutions with attentions or vice versa. It's a mix really, but if you just take a pure VIT without convolutions, you get really strong performance. Okay, and I said that this VIT could learn good representation for image-related tasks like object detection and image generation. But further than that, what is now becoming the norm in computer vision tasks is, so if you remember, for example, last week we talked about YOLO and this very specialized architecture where we would have to predict the positions of the rectangles, the position of one of the corners together with the width, together with confidence scores and so on. Actually, when you think about it, you can reformulate that output as a sequence of text that you have to produce, which would correspond, for example, to a text which capture the coordinates, but in text, of the rectangles. Or if you have to predict a segmentation mask, you could formulate that as a polygon, and you just produce as output the coordinates of each node of the polygon. And so you can then see that, okay, you can transform many of these computer vision tasks as a task in which you have to produce a sequence. Okay, and so that means now you can have a same architecture, just producing sequences of things that you can reuse to solve many tasks. And this is what is done, for example, there in the segment anything architecture by Meta, where they achieve very, very strong results by just having a very big image encoder, which you see there, which is a big VIT, which will have produced a list of tokens, all these little small patches. And then from these tokens, you have other transformers. You could have a decoder transformer to produce a mask or a prompt, which you could also condition, for example, on a prompt, which then would be based on text. to produce a list of coordinates, for example, for this, depending on the content, of course, of the prompt. So this is really nice because this really enables detection of anything. So with this architecture, you can say, I want to detect scissors, even if you have not trained specifically a network to detect scissors in images. Okay, you can specify at test time the classes that you want, the content that you want to identify. Okay. And these are other results.
This is SAM, the Segment Anything model. It's the latest from Meta AI's computer vision research team. SAM lets you automatically select individual items from an image. You can click on what you want to select, or you can let it figure it out by itself. So what's going on under the hood? Basically, SAM can figure out how to select any item in a picture, even if it hasn't been specifically trained on similar images. This is going to help AI systems understand the world better so they can help us get more done. In the future, you could just look at something through your AR glasses, and SAM can pick out the items and even turn them into 3D objects. So you'll be able to pull something out of a photo or video and make it come to life, share it with friends, or remix it into something else entirely.
Okay, so this is actually an old network from 2 years ago. Since then, they've released Segment Anything 2, where it's really even more incredible. But basically, what is you can if you so the change of mind that you should have is that if you can express also the task as tokens, then you're good to go to solve anything. Okay, and as long as you have learned a very good model, which, for example, on images would learn a very good representation of images, or on text with regular transformer, or maybe jointly with multimodal transformer, which understand both images and text, then you can start. You don't need to predefine anything. Okay, you can just work directly at the level of the tokens that you've learned. Okay? Or you can look at the paper if you want.
Share it with friends, or remix it into something else entirely.
So you can Google this. You can Google the name of the authors, or just type Segment Anything. You will find a Meta promotional web page, but also with a link with a scientific paper. Questions? Remarks? Nope? Okay, then that's it for today. Thank you.